Okay, so we continue the lesson. If you remember, in this new chapter, we learned about the notion of primitive functions. I told you that a function capital F is said to be a primitive function for another function little f if when you take the derivative of this function, it becomes this function. Yes, for example, f of x, capital F of x equals to 3x squared is a primitive function for this function, x to the power of, the other way around. X to the power of 3 is a primitive function for 3x squared. Yes, because if I take the derivative of that function, it becomes this function. And of course, you know that we learned that not only this function, but if I add any constant to it, it also becomes a primitive function to this. So immediately we can find infinitely many of them. But we also told that this is always the case. If someone finds a primitive function for a function, every other function which is going to be a primitive function cannot differ that much from this function. They can differ at most by an additive constancy. And then I told you that for the time being, you have to be patient, take this as a mathematical curiosity without that much application to it. The reason that this becomes important is because we want to discuss about integrals and to see how these two problems are connected. First, I want to introduce an integral by the notion of the area below the curve. So that's a good starting point. So let me clean this. The point is, I will try to sketch something here for you, but might be it would be better at some point we go to GeoGebra and have better pictures. So let us say that I have a function. So let us make it simple. Y equals to f of x. And then you have a starting point here, point A. I draw a vertical line here. And then I have a final point here, B, and I draw a vertical line here as well. And then you see that there is a region here which is bounded by three straight lines, these two vertical lines and this horizontal x-axis, and a curve. And then we want to understand how we can calculate the area of this region. Okay. So the way that we want to describe it is actually you need to learn the concept, because calculation integrals and understanding the concepts are more or less a little bit different. So the idea is this. Instead of because this is not a straight line. If it was a straight line, I can break it into triangles, and then I can calculate the area of each one of those triangles and then add them up. But the problem is that, unfortunately, this is a curve. Okay, so what we do here, this is the idea. You start chopping up this interval to smaller pieces. For example, let me take this point x1, and then this point x2, x3, and then x4. So I will keep all of them equal, this in size, okay? And for consistency of my notation, this is common that I call the first one x0, and in this case, the next one becomes x5. Okay, so this is just for consistency of my notation. So what I am doing in this case, I had one interval and I decided to divide my interval into 1, 2, 3, 4, and 5 smaller intervals. Might be I have been a little bit careless, but my intention is to keep the sizes of all of them the same, okay? And then what we do, we start drawing vertical lines here from these intermediate points that I described. And then, for example, here on this interval, I focus on the minimum of my function. So you see, if you are looking at the graph of your function within this interval, I hope that you agree with me, this is the lowest possible value of my function. And then what you do, you complete a rectangle there. So it means that I find the minimum of my function on this interval wherever it is, I draw a horizontal line, I construct a rectangle here. Okay? And then I do this process. So I go to the next subinterval, I find the minimum. Don't focus on why minimum, not maximum. I will discuss a little bit about that later. So here, this is the minimum value of my function. And then I complete the rectangle here. So I will get another rectangle. Yes? I will do this process. So for example, if I go to the next interval, I have this point, and then I will do the same thing here, and then I will do the same thing here. Okay, so this hatched area is not exactly what I demand, but it is not a bad approximation to what I demand, yes? It's fairly close, except I am overlooking these small parts that you see. So here, I can call this area number 1, and then I can call this area number 2, area number 3, area number 4, area number 5. And then let us call the area, the demanded area, A. I would say that it is not that unreasonable if I say the area that I am looking for is approximately the sum of these areas. Yes? Of course, you see that how much error that I am making. Yeah? So let me change my color. This part and this part, that part, that part, they have to be considered, but I overlook them. So this is the sum of these red parts is the total error that I am making in this approximation. Okay, but before going a little bit further, let us try to put this in a general setting. So here I decided to divide the interval into 5 pieces, but in the future I want to divide it into general n pieces. Instead of dividing it to 5 pieces, I want to divide it into n pieces. If I decide to divide it by n pieces, the first one I can call it x node, yes, which is my A. The next one I call it x1. The next one I call it x2, and I will continue. And the last one, which is the nth one, I call it b, I call it xn, and it is clear the previous one is x sub n minus 1. Is that clear? So instead of having 5 of these subintervals, if I have more and more of them, say I have n of them, then this would be the list of my numbers. Yes? And this distance between these two, or I told you that I want to keep all of them the same, this I call delta x. It means that I am saying that this is the change in x. Okay, so I call it delta x, this length. So for example, for this case, if I ask you what is delta x, you will tell me that I find the total length and then divide it by 5. Yeah, so you say that what is the total length from here to here? You say from here to here is b, from here to here is a, so what is left for me here is b minus a, and if I ask you what is delta x, you will tell me this is b minus a divided by 5 in this case. But in the case that I have n subintervals, can you tell me what happens for my delta x? What? Hello? What happens? Yes?
Isn't it just b minus a divided by x?
Divided by?
By n.
N, yes. So that is delta x. But let us, for example, here, if I ask you what is x1 in this setup, you will tell me that x1 is a plus 1 delta x. A is here. If I add delta x to it, I will come to x1. But how can I go to x2? By starting from a, I can start from a, but add 2 delta x. I will reach to x2. If I ask you what is x3, you will tell me that a plus 3 delta x. So if I continue and say what is x sub k for any k, what do you write? A plus k delta x, yes? So let me write the formula, and then this is A plus delta x is that expression. So this is k times b minus a over n. I am just making things ready so that we will use it. Okay, but this is not very strange. So do you agree with what I'm writing, yes? Okay, now I want to write this as a sigma. Okay, for 5. If I want to write this as a sigma, before doing that, I want to ask you in this picture, what is A1? What is the area? If I ask you to calculate the area A1, how do you do that? You take the width and then multiply it by the height, yes? The width, I assume this is delta x, but what is the height? This function is f of x, and this point is a. So this height is how much? F of a. So you multiply f of a by delta x. So a1 is f of a times delta x. But I told you that for consistency of notation, instead of a, I can write x node. And if I ask you what is delta x, you have the general formula for delta x. Now let me ask you once more. What is a2? a2 is this area. It's a rectangle. So what I do, I will take the width and then multiply it by the height. But what is height? Here is x1, and I want to see the height. This is my function f of x, so the height becomes f of x1. So it becomes f of x1 multiplied by delta x. Yes? And then I hope that you agree with me, for the general case that I have n points of partition, I will reach to the last rectangle. In this case, it is A5, but if I have n points, it becomes AN. Okay, can you tell me what is AN in this case, if you follow the pattern? Yes?
F of x sub n minus 1
Yes?
times delta.
Times delta x. Yes, is that right? Okay, so now if I add them up, I can say that my area is approximately the sum of these areas. But I hope that you agree with me, I can write it as a sigma, and then I write capital A, and then I put sub k here, and run k from 1 to n. Do you agree? What I have written here as a sigma is just this expression. Because if I ask you open this sigma up, do you remember? You have to replace k with 1. It gives you a 1. Then go one step at a time. It becomes 2. Put 2 here, it becomes a2. And then go one step at a time, a3. And then when you reach here, you stop. So that's it. Yes?
Sorry, I don't recall us using sigma before. Can you...
Sigma means, so that's exactly what I mentioned. So if you have a sigma notation, sigma means sum, and then you have a counter for the sigma, and it starts from somewhere, say 5, and then it goes to somewhere, say 7. These two numbers should be integers, and this number should be less than or equal to this number. And then, for example, I write 2k squared plus 1. And then I ask you to open up the sigma. What does it mean? It means that in the expression in front of the sigma, there is a k. You replace this k with the lower value, and then replace k with one higher, 6, and then continue until you reach to the final limit. You get some numbers, you need to add them up. Yes, so this becomes what? 2, 5 to the power of 2 plus 1. I replace k with the lower limit, but then I go one step higher. It is k6, I put it here. So this becomes 2 times 6 squared plus 1. And then I go one higher and I reach the limit, the final limit. So it becomes 2 times 7 to the power of 2 plus 1. And then I have to add them together. You get a number, that number is this thing. Yes? So this is a compact way of writing large sums. Okay, but instead of a sub k, what can I write? K goes from 1 to n. So a1 is f of x0, a2 is f of x1, and delta x is in common, so I can write a delta x here. but instead of a sub k, you see that I should write f x, but with one index lower. If it is 2, it is 1. If it is 1, it is 0. If it is n, it's n minus 1. So this becomes k minus 1. So what we get is this. It's a reasonable approximation to say that for this function, this area that I was looking for is an expression like this. Yes? But the problem is that what can I do with the errors? Of course, it is an approximation, might be it is reasonable, but what can we do with the errors? The point is that I start making the intervals more and more. So here, when I make the intervals 5, you see that I have these errors. But let me change my color, for example. Instead of making it 5, so let me clean this and make it 10, for example. For example, let me divide every one of them into an extra one. So this is x0, this is x1, x2, x3, x4, x5, x6, etc. And I do the same thing. So what will happen? Now my first interval is this one. So then what I do, I will complete so I will go up, and on this interval I find my minimum, which is still this one, and I complete my rectangle, which is this one. Okay? And I go to the next interval, and I will find my minimum, which is this one, and I complete this rectangle. And then I get this one. Yes? So what happens, I hope that you agree that the leftovers in total is smaller than the previous leftover. Yes? Because you see that in the previous case that I had only 5 partitions, then, for example, for this case, this red part was my error. But now I am including one part of it. These small parts are my error. So this is no longer the part of my error. So it is eliminated. So the error that I am making becomes smaller. Okay, so for example, let us go to the next one. So if I do that, okay, and then I complete my rectangle, so that would be one of my rectangles now, and then this becomes another one. Okay, and then you see again, I am covering this part now. I didn't counted it in blue parts, so that was really part of my error. But now when I do that, that part of that error is covered. Of course, I agree with you, still these 2 parts are left. But the whole point is that if I start increasing the number of points, I hope that you agree with me, the error that I am making becomes smaller and smaller. I can show it with GeoGebra that this is really working. Is that understandable? Okay. So, okay, can you tell me what I'm going to do? So we learned that my goal is to try to get closer and closer to the area as possible. But I also observed that by increasing the number of partitions, I am making my errors smaller and smaller. So idealistically, if I want to really reach to area A, what I'm supposed to do, for example, if I divide this to 1,000 points, then of course the error becomes smaller. So instead of running k from 1 to n, I cut it from 1 to 1,000. Of course, still it is approximation, but it is a better approximation. If I make it 10,000, it still becomes better, yes?
So in this case, we just use limit.
Yes, so it means ideally I need to make n
Go to infinity.
infinite, yes? So when I make n infinitely large, then hopefully you agree with me, there are no errors left. Intuitively, I'm not proving something. By the way, this is the way in higher mathematics, this is the way they define the area. Okay? So I'm just converting up somehow the logic, because at the level of high school, we assume that you know the area, You want to use the notion of area to understand integrals. But the logic is completely different. Integral is an abstract object, so you can calculate integrals and then you say that, okay, this integral is defined to be this area. But I'm not following that logic, okay? So then let me write this one. So the final observation is that if I take that sum, k goes from 1 to n, f of x sub k minus 1 delta x, and take the limit of that, n goes to infinity. This seems reasonable, yes? So if you learned what I told you here, if this formula, even though might look complicated, but if it is reasonable for you that this somehow identifies the area, so I am done. Are you happy with this or not? Yes? Is that okay? So this formula seems reasonable. But there is a problem with this formula. What that problem is? Yes? Yeah, exactly. So I just convinced myself that if I make n infinitely large, then I have the area. But the problem is very simple, practical problem. How can I chop this interval into infinitely many pieces? Even if you have supercomputer available for doing a loop infinitely many times, you need infinitely many hours. Okay, so it's not possible. So even though it looks nice, but apparently it is a dead end. It is not going to work. Okay? But the point is that I just want to show you with one example. This is not in the book, but I think it is good to know. I want to show that the situation is not that bad. Okay, even though this formula is not a good formula for calculating what I do, but it is better than you might think. Okay, so let me just do that. Okay, what I want to do, I want to give you an area which you already know and calculate it using this formula. For example, let me take this area. Let me make it very simple. Okay, so this is x and y. I draw this bisector, which is y equals to x, and I start from 0. Say, let us make it very simple, up to 1. And I go, so let me make it a little bit bigger so that we can understand what's going on. Okay, here. And then I want to go vertically up, and then I have my triangle here, yes? This is y equals to x, and this is... I want you to calculate this area. Of course, you can immediately answer the question, hopefully, because this is just a simple triangle, okay? So what's this area? What is this area? From here to here is 1 unit, and from here to here is how much? Because this line is y equals to x. So what is this height? Yes, what is the height?
0.5, no, 1.
No, the height is also 1.
Yeah.
So the area becomes 1 times 1, as you said, 0.5 square area units. So this is simple. But I want you to do the same thing, but this time using this complicated formula to understand that what is the meaning of this. Okay, let us try to do it together, okay? So how should I do that? The starting point, okay, let us compare everything with here. So what is the starting point? What is playing the role of A? Yeah, it's there. What is playing the role of A here? So compare this picture somehow in your head with this picture. So this curve is no longer a curve, it's this straight line. And this vertical line going from B, now this is this vertical line going from 1. And of course, there is no vertical line here that starts from 0. So if you compare these two, you see that A is 0, B is 1. Yes? And then what we want to calculate, we want to calculate f of x sub k minus 1. And I need to calculate delta x. But delta x is easier. Let us do that. If you see the formula for delta x is the final point minus the initial point divided by n. So in this case, my final point is 1, my initial point is 0 divided by n. So this means that my delta x is 1 over n. Yes? And now I want to calculate x sub k minus 1. The formula is still on the board, but this is for k. Can you tell me what should I write for k minus 1? This is the formula for x sub k, and k appears here. But now I want to write x sub k minus 1. So what should I do? Yes? What should I do? Thank you very much. Instead of k, what do? I put k minus 1. So what happens? I have a here, which is 0. I have k minus 1. I have b minus 1 minus a divided by n. Okay, this 0 is 0, and 1 minus 0 is 1. K minus 1 is multiplied into the numerator. So hopefully you agree with me that x sub k minus 1 is k minus 1 over n. Yes? The next thing I need f of x sub k minus 1. But what is my function? Y equals to x means my function f of x is equal to x. So I need to calculate f of x sub k minus 1. Yes? But f of x sub k minus 1 is x sub k minus 1 itself, because this function takes x from you and gives it back to you. So when I put x sub k minus 1 in it, it gives that number back to me, but I have already calculated this one, so this is nothing except k minus 1 over n. Yes? So now everything is ready, at least. I put them back into this formula. So I would write a is equal to, I write the limit, n goes to, n is supposed to go to infinity, and then I have a sigma. The counter is k, starts from 1, and it goes up to n. Okay, instead of f of x sub k minus 1, I simply put k minus 1 over n. Multiplied by delta x, which is 1 over n. Okay, so at least I wrote the formula. Then the problem is that, can I really calculate this limit? This is one of those cases that we can. This is one of those few cases that we can. Okay, so how should I calculate that? If you don't mind, let me simplify this a little bit. So this becomes the limit equals the limit sigma k goes from 1 to n, and then I multiply the numerators, it becomes k minus 1. I multiply the denominators, it becomes n squared. And n is supposed to go to plus infinity. The hard part of this calculation is calculating this sum, which is not always possible. And sometimes, and most of the time, it is impossible. Okay? But this is one of those few examples that I can show you how we can calculate this sum. So how should I do that? Let me call it S. I want to calculate this sum first. And then after that, I calculate the limit of my sum. Because sigma notation is not a good idea if you want to manipulate, if you are not very familiar with this one, let me open up my sigma so that you can see this, there is nothing mysterious going on. But help me to open up the sigma. What I'm supposed to do, I have an expression in front of my sigma. The counter starts from 1, goes up to n. And I want to open up the sigma. So what I'm supposed to do, I replace k with the first value, and I replace k with the next value. I replace k with the next value. And I continue this process until I reach to the final value. And I replace k with the final value. And whatever I get, I start adding them up. Okay, I want to wait. Is that understandable? What I have done is clear or not? So I replace k with the first value, replace k with the second value, with the third value until the end, and then I add them up. But I can simplify this because no one writes this, because this is what? 0. 1 minus 1 is 0. 0 divided by anything is 0. But 2 minus 1 is 1 over n squared. And then 3 minus 1 is 2 over n squared. What is the next number? The next number is 4 minus 1, which is 3 over n squared. And if I continue this process, I cannot do anything with that. I have to write it down. But now you see that I have every denominator the same, so I can take the common denominator to be n squared, and I start adding up these numbers. So 1 plus 2 plus 3, but up to which point? Up to n minus 1. So if my function, you see, my function is a very simple function, and still the calculation is quite lengthy. But at least it is possible. If I change this function slightly, for example, if I'm making it x squared, then what will happen? Squares of numbers will appear. Still it is doable, but harder. But let me change x to a square root of x. Then a square root of 1, a square root of 2, a square root of 3 will appear. Then that is a dead end, because I do not have any formula for that sum. But do you remember there is a formula for this sum? You have studied that in Math 2C. What is the name of this kind of sequence of numbers going one at a time? There is a name for it. We had two kinds of series, yes? It's called an arithmetic progression, yes? Do you remember something like that? So you go, for example, an arithmetic progression is 5, I go 3 at a time. So 8, 11, I don't know, 14, etc., etc. Okay, so that's an arithmetic progression. Do you remember we had a formula for S sub n? We had a formula how to add them up. It is not always possible to add all kinds of series. But if this is an arithmetic progression, we had a formula for it. And the formula, I want to write it for you here. So the formula S means the number of items that you see. The number of items that you see is n minus 1 divided by 2, multiplied by the first number plus the last number. Okay, don't worry about that. So you need to trust me on that if you have forgotten. So the sum of these numbers become that. And then this minus 1 and that 1 are cancelled. N is left. I multiply it in the numerator. So this becomes n squared minus n divided by 2. And if you don't mind, yes, this is capital S. So I use a small s so not to confuse. Okay, so that's it. But this is only for the numerator. So I put this inside the numerator, and then what happens, it becomes n squared minus n over 2 divided by n squared. And then I multiply everything by 2 to get rid of partial fractions, so this becomes n squared minus n divided by 2n squared, and this is your capital S. So if someone, I want you to understand, if someone asks you why calculating the area using the problem is hard, of course it is lengthy, but that is not the main obstacle. The main obstacle is that if this function is a little bit complicated, calculating this series is more or less impossible. Okay? Now the last step is to take the limit. Do you remember? I am supposed to calculate the limit, but for simplicity I broke this down here and calculated it, and now the last step is to calculate the limit. By the way, I can calculate the limit here. So, but this principle, you should tell me how to do it. I want to take the limit. We studied this a little bit. So n squared minus n over 2n squared. The first thing comes to mind, you see I factor an n out, at least one of these n's are gone. So I factor n out, n minus 1, and then I have 2n squared, n goes to infinity. and this n and that n are gone. So what happens? This becomes the limit of n minus 2 divided by 2n. N goes to infinity. And by the way, what can I write? Let me just do it in my head. There is no space. I divide n by 2n, which is 1/2. And I divide 1 by 2n, which is minus 1 over 2n. Okay. Yes? Okay, can you tell me what is this limit now? When n becomes infinitely large. Yes?
1/2.
1/2. Why? Because 1/2 is constant. It has nothing to do with making n large. But when I make n large, I am making this fraction small. And if I make it extremely large, it becomes extremely small. So in limit, the number becomes 1/2. And this 1/2 that you see here is exactly that 1/2 that you calculated in a matter of seconds. Okay? But don't underestimate this process, because instead of giving you this function, if I give you this parabola and ask you the same question, yes, and ask you what is this area, there is no formula for that. Okay, before Newton, this was the only way of calculating this area. And by the way, Archimedes did that perfectly, exactly, by something similar. I think Archimedes is BC, yes? Somehow BC. So I mean, he was so genius that he was able to calculate this area from 0 to 1 of the function y equals to x squared exactly, not approximately. Okay? But he didn't use rectangles. By the way, this method is called the method of exhaustion in mathematics. Okay? We used rectangles to do that. I think, if I remember, I forgot. I think Archimedes actually used triangles somehow, but the idea was something like this: approximating the area with triangles and making the number of triangles infinitely many, so that the errors becomes smaller and smaller. I don't want, because it will be very disturbing you, but that would be a good challenge for you if you like these kinds of problems. So you need to be able to do something like this, but you see that it becomes more involved, but it is doable. And then you find this answer. Okay, and I will tell you something and I will end the lesson here. But this was Newton who was so genius to understand there is a connection between primitive function and the area. You see that what I have offered here, you don't see any idea of primitive functions coming in. Yes, so I just calculated some area. But Newton realized you can do something very simple, or fairly simple. Ask yourself about a primitive function for this function. What is a primitive function for x? How much you remember? What is a primitive function for x? A function whose derivative is x, yes?
Half of x up to the
Power 2. Yes? So do you remember, if I ask you what is a primitive function for this one, the answer was, we practice a lot about this. That is a primitive function. And then Newton tell us, where is the starting point 0? Where is the final point 1? Put these numbers inside your primitive function. Put 1 here, it becomes 1 over 2. Put 0 here, it becomes 0. And subtract them. And when you subtract them, you get your answer. And that is 1/2. And that is actually the genius of Newton, who realized there is a connection between, somehow he realized there is a connection between derivative and area. Because Leibniz realized that there should be a connection between the slope of the tangent line and derivative. But now we learn that the notion of derivative gives rise to the notion of primitive functions, and then he also realized that there is an idea, there is a relation between a primitive function and the area. Okay, so this will be the topic of the next lesson. So that was the motivating. This part is somehow included in the book. If you see these pictures, you see something similar in the book. But the idea is that I want you to understand this. Do you remember, even when I started talking about derivatives, in the first few lessons, I didn't use the differentiation rules. Do you remember? What we used the formula as the limit. F of a plus h minus f of a divided by h goes to 0. And then little by little we learn that this is really tedious if I want to calculate the derivative all from scratch using this formula all the time. The philosophy is more or less the same thing. Here, I found a formula in the form of a limit, and then by one example in details, I just try to motivate you that yes, if you want to follow that rule for every function, it is sometimes even impossible, or even if it is not, it is lengthy. So then the idea becomes, is there another way to calculate this limit? Okay, for this situation, we learned about differentiation rules. And now, because of this theorem that Newton discovered, we can use primitive functions to calculate these limits. So that will be the topic of the next lesson. I just wanted to motivate you this definition and try to tell you that this kind of limit is important in mathematics, exactly as before. This kind of limit is important in mathematics. So whenever something is important in mathematics, you see that this happens in different places. Usually mathematicians give that a name and try to study the property of that thing. Okay, any questions? Okay, we stop here. Thank you. Might be we don't stop here. So let me see that what we can do in GeoGebra. It's also good to know. I think there are some functions, at least you can see that this is working in practice. Let me see. So let me write area. Yes. No, that's not good. So, okay, let me write integral. Integral, yes. Let me see if so for example, if I go here, no, I want to draw the sum that I introduced. Remember, I told you that I start with minimum. That is called a lower sum. So let me just do that, okay? So I write lower sum. Okay, yes, it is here. So lower sum of my function. What was my function? My function was x. Let me make it more interesting. So my function, let me make it x to the power of 2. Or let me write the square root of x, okay? Square root of x is probably better. That's the example in your book. And then, for example, I go from 0, and then I go up to, say, 16. Yes. 16, and then this asks you about the number of rectangles. How many rectangles? Let us make it 2 rectangles first. Okay, so this is what you get. And by the way, it is good to draw the graph of the function itself so that you can see that square root of x. Okay, so that's the graph of the function. And of course, this minimum value is 0, so this is why you do not see any rectangles at all. Yes, is that clear? Because this is from 0 to 16. When I say I need 2 number of rectangles, so this will divide my interval to 2 pieces, one from 0 to 8, one from 8 to 16. Yes? And I was supposed to take the minimum value of my function on each interval. From 8 to 16, the minimum value is this, so they complete this rectangle. But from 0 to 8, the minimum value is 0. So this is why you see a degenerate rectangle there, yes? Okay, let me go back here and increase the number of rectangles. So for example, let me make the number of rectangles to be 4. And then do the same thing. So now I have 4 rectangles. By the way, this is calculating the sum of these areas of these rectangles. Yes? And if I make it, I don't know, for example, 8, what is happening? Okay, and then you see that every time I am making the error smaller and smaller. So the area now getting close to 38 now. Okay? And then let us make it, who cares? This is GeoGebra. Make it 100, yes? Okay, so it is already close to the area. So if you see that, this is not exactly the area. If you don't believe, you can zoom in. And then you immediately see the errors. Yes? So you see the errors. Okay, but let us also make the GeoGebra suffer a little bit because it's actually torturing my soul that much. I don't like this. Okay, but let us make it 1000. And this is already a continuum, yes? So it is very, very close to the area. Yes? And then, but by the way, this is not exact area because if you see that when I zoom in, what is happening? You see still I see the deviations. These are the errors that I'm still making. So when even if I make it 1000 rectangles, but the errors are not zero. And still you see these errors. Is that understandable? Okay, but let us see how much is the value of the function. Yes, it is getting close to 42 now, so this is more reliable. So it's already good, you know. Might be you cannot visual. Let us make it 10,000. Is it working or not? At some point it starts suffering, yes? You see that when I make it 10,000, this number didn't change at all. So the error was so small that when I went from 1,000 to 10,000, 42 was left the same. So it means that, yeah, even if 10,000, it's already, but still you see that if I zoom in, it is probably not exact. You should be able to detect it. It depends. Yeah, it's not that easy to detect the error this time, but we just continue pushing and pushing. Yes, and still we continue. You shouldn't give up, especially to GeoGebra. Yes, and now errors are appearing again. You see, the errors are still there. Yes? But we are getting closer to the real value. I hope that this demonstration shows that this is not really unreasonable to calculate this. By the way, I just made it 10,000. Let us make it 1 million, I don't know, 10 million, and let alone to infinity. So hopefully you agree with me, this is a reasonable way of defining the area. Yes, please.
No, I tried using lower sum to infinity. GeoGebra still has errors then. So.
Yeah, because I think for infinity it doesn't work.
Yeah.
But I don't know if we make it 1 million it will work or not. Yeah, let us torture him. So 10,000. It's now let us make it 1,000. Well, it's working. It's weird. So 1 million. No, I don't think it works. Or it worked. I don't know. No. But anyway, I hope that you agree with me. By the way, let us. Now you understand what is the Newton's rule. Can you calculate it using Newton's rule? Of course, I will teach you that later. So do you remember, if I ask you what is a primitive function, so my function was a square root of x, my lower limit was 0, my higher limit was 16. So how do I need to calculate if I teach you next time? You need to ask yourself about the primitive function for a square root of x, and that is also something we practice a lot. Do you remember? We write x to power 1/2, and then we write x to the power of 1/2 plus 1, and then I divide it by 1/2 plus 1. So if I do this calculation, it becomes 2/3 x to the power of 3/2, which I write it as the third sign, it becomes x square root of x. Okay, and then I put 16 here. 16 is 464, 128/3. And when I put 0, it is 0. When I subtract them, so this is the exact answer. So GeoGebra gave us what? 42, let us check. According to my calculations, 123 divided by, no, 128 divided by 3. So this is the exact value. You see, so even when I make it, I don't know if this is really 1000. Is it working here or not? Let me make it 1000. And for 1000, do you remember what was the approximate value? So you see, it is different. 42 is 42, 6 is the same, but 3 is not stable. So even if you make it 1000 rectangles, you have 3 digits correct. The 4th digit turns out to be wrong, because this is exact value. Okay, so let us stop here. Thank you.